Hello viewers and welcome to another episode of Space Science with Python. In our last session we were talking about the opposition effect. So in our small science video I talked about how the apparent magnitude changes for different phase angles. And the session before we computed the apparent magnitude of the near-Earth object 433 Eros. And today I would like to combine these things a little bit and would like to show you how the apparent magnitude changes for a theoretical object. So how are we going to do this today? Well, let's move to my very cool drawing skills. And we will make things quite easy today. So this is the sun here in the center, or let's say the illumination object. And we will put the Earth at some coordinates. So somewhere like maybe here. So here's Earth. The distance is of course 1 AU. And we will compute everything in 2 dimensions. So we will get rid of the z dimensionality. So we will have x and y, but z will not be there. So everything in polar coordinates. And then we will put or place our object, so some NEO or asteroid, somewhere, let's say at, for example, 2 AUs. So like here. Yeah, so this is our NEO. And we will move then the NEO for 360 degrees. So we will compute the apparent magnitude at this particular position, and then here, and so on. So for each position, we will compute the brightness, and we will assume it's a circular orbit. So it has an eccentricity of 0 around the sun, and the Earth will be steady state. So the Earth will not move at all, so that at the end of the day, we can compute the apparent magnitude for different values or for different positions of the NEO, and leave Earth where it is here in the drawing. So yeah, quite simple. So what are we going to do? So first of all, we need to import our standard libraries. Of course, we need SpicyPy, or actually this time we do not need SpicyPy, but what we need is our auxiliary function in cell number 2, which is which contains the apparent magnitude in a module called photometry. Now I see this cell has been executed, so let me restart just the kernel quite quickly. And in the meantime, I can show you here that we have now this auxiliary folder, and here in photometry.py we have the apparent magnitude. So we keep everything quite clean. I know it's not like a dedicated library or something, but I think this is still fine. So let me execute the first cell. So number 1, this is number 2. Okay, this is now quite apparent. And now in cell number 3, we are creating some, let's call sample properties for our NEO. So we set an absolute magnitude of 10. So just some random value. And we set the slope parameter g to 0.15, which is like the default value for NEOs if we couldn't determine the slope parameter. And then we set something like, I just call it the static observer vector. So the position of Earth, it's at -1, 0. So this is just in 2 dimensions and given in AU. Let's move to cell number 4. Also quite simple. It's again some kind of auxiliary function that helps us to convert from polar coordinates to Cartesian coordinates. Just call it polar to cart. So with the angle phi, and the radius is per default at 2. So in this case it's 2 AU, and we will move phi from 0 to 360 degrees. And then we can move to cell number 5, where we are simply creating a NumPy array from 0 to 360 in 1,000 steps, and then we create the corresponding vector. So this is like the vector from the illumination source, so the sun, to the object, so illumination to object in a list comprehension, and then afterwards we invert it, because as you may recall from the apparent magnitude function, we need always the vectors from the object to the illumination source and from the object to the observer. So here in cell 5, we also invert now all the results, so that we have the object with the vector from the object to the illumination source. And then afterwards in cell number 6, we are then computing the vector from the object to the observer, where we do some simple yeah, where we do some simple vector computations. Now cell number 7. Oh, I should execute this one here first, and then yeah, I probably didn't execute it at all. I just see it here. Cell number 3. Yeah, it now changed a little bit, and now here. Now in the next cell, we are computing now the apparent magnitude for our different positions. So again, let's move here back to the drawings. So we have a list comprehension where we compute the apparent magnitude at this position. So here we have an illumination of the NEO. Now then here, here, and so on. Of course, the distance changes, the phase angle changes, and accordingly, the apparent magnitude changes as well. So we have a list with the apparent magnitude for different phase angles and different distances, respectively. Now we do this here in this cell, and then afterwards we can also now compute the phase angle, because maybe we would like to compute the apparent magnitude versus the distance, also the phase angle. So let's go quickly back and let's reevaluate what the phase angle is. So just as a small reminder, let's remove everything we do not need. So let's make a new neo, like here, for example. And the phase angle is simply the angle between the object and the illumination source, so the neo and the sun, and the object and the observer, in our case, the Earth. So this is the phase angle here. And the phase angle can vary between 0 degrees and 180 degrees. Yeah, so 0 degrees means the object is at this position. Let me take a gray color again. The object is here. So this is the opposition. So the vectors are parallel and the angle is 0. And 180 degrees would mean that the object would be here. So perfectly between the sun and Earth, but the apparent magnitude function, the HG function, is only valid between, yeah, let's say the opposition, so 0 degrees, and around 120 degrees. Yeah, so this is an empirical equation. So you have always to be careful when and where to apply this function. But yeah, let's compute also the phase angle now here. And now what we can do is we create a simple plot. We create the plot where we show the apparent magnitude versus the angular position of the NEO in degrees. So we execute this cell. And what we see now is this plot. So we see the apparent magnitude. Just a small recap. Smaller values correspond to a higher or to a brighter object. And the other way around, a larger value corresponds to a fainter object. And we see here the angular position of the NEO in degrees. So this phi angle I was just computing. So we see here, as seen from Earth, yeah, values, how they change. Then we have like a maximum. So this is the peak. So peak brightness at 11.5. And then it faints again. And then it has a second peak again here somewhere. Now, let's think a little bit how this happens and why we have two peaks. It's not really like magic or something, but we will get an understanding just in a second by computing showing the apparent magnitude versus the phase angle. So let's compute or visualize this plot here. And now this is a little bit more difficult to understand. It's like a phase curve. We have here the phase angle in degrees that varies between 0 and around 30 degrees, and the apparent magnitude. And you see here the phase angle is 2 times at around 0 degrees. And at one point we have 11.5 magnitudes, and here 14 magnitudes. And this is not so difficult to understand if we go back to our small graph here. So let me remove everything again. We have, of course, yeah, something like 2 opposition points. The one is when the neo is here. So this is like the straight line. We have the vector to the sun and to the Earth, which is like here 0 degrees. And the same thing, the same geometry applies if the NEO is 180 degrees on the other side, because then again the vector from the NEO to the Earth and to the sun, they show also in the same direction. So the opposition effect applies also here, but of course, from an observational point of view, it's extremely absurd to speak of an opposition effect because we cannot really observe it, right? So it's virtually impossible because the sun is, glaring everything over. You don't see it during the daylight. So despite the fact that the function is valid between 0 degrees and around 120 degrees, you have also to consider where the object is with respect to the sun. So if you are doing something like a planning observation or so, then you have also to consider something like a cone from the Earth to the sun, where everything is more or less invisible because it's broad daylight or it's dawn or dusk. And depending on your little bit your settings and so on, there are different, let's say, philosophies, but you could say, okay, I assume everything is invisible that is within, let's say, a cone of 30 degrees, for example. This is like a random number of 40 degrees. And this will be important later on if we are considering what kind of objects are observable or visible or detectable at all from Earth. So of course we have values for NEOs that are virtually everywhere, like here or here and also here, but in fact they are in a way dead to us. The only observational area is the night direction, so everything that goes into this direction. Okay, this drawing is a little bit chaotic now, but I think you get the gist. So this is like the reason why we have these two opposition effects, but the brighter one is the one of interest. Now, why is the other opposition effect a little bit fainter? Well, we can simply compute the distance between the object and the observer and then plot again the phase angle versus the distance. And then we get this plot here where where you see the phase angle versus the distance between the NEO and the Earth in AU. And of course, the phase angle has 2 times 0 degrees, one at the opposition directly here, and the other one when it's here. So these are the two geometries you need to consider. If you would like to emphasize this image a little bit, you can, for example, scale the size of the plot depending on the brightness or so. But this is maybe up to you as a small homework. That's everything for today about the opposition effect. I hope you learned something, and also you have some fun now applying this function, because again it's very complex with all the variables and the phase angle and distances and so on. It's quite multidimensional. But in the next video we will use the entire NEO database to compute the brightness distribution on our night sky in a sky plot, to get a first feeling where are the objects currently, and are they currently visible, and if so, where, when, and in which magnitude range. So this will be we will do this in 2 weeks. So I hope in the meantime you will get through this script a little bit and the other scripts. Again, everything is available on GitHub, and until then I'm always available for any questions, and take care and see you next time.